Let's start. Okay, so couple of quick announcements. So homework 3 is out and it will be due Monday, the 23rd of October. Okay, so that's a while from now, but as you know, there's a break next week. So we have, so I wanted to give an extra weekend after the break so that you have some time to work on it. Okay, so it's due on Monday. Okay, and so as usual, start early and so on. Okay, and also the project topics will be out right after fall break. Okay, so this, as I said, it will be an implementation project. Okay. So today the writing is not going to look as crisp as normal. I don't have my iPad, I'm using something else. Okay, so bear with that. Okay, so but project topics will be out after fall break. Okay. And the style will be that there will be some research paper and you'll have to get some ideas from it and implement it. Okay, so and there will be problems on various topics. So you can pick which one you want. There will be about 10 projects. Yeah.
Two minor questions. First one, this is the project that's outlined in the syllabus, right?
Yes.
A big project.
This is, it's not very big, it's about the size of a homework. That's how much it counts to your grade.
And the other half of my question was, are we going to have homeworks at the same time as the projects throughout the rest of the semester?
Yes. Because, so you will realize that the next, starting with homework 4, homeworks will be a bit more easy in the sense that they're supposed to just be whether you've understood what's going on in class. Actually, the topics we cover will be trickier. Okay, so the homeworks are just going to be like whether you've understood stuff in class and so on. Okay, so
So what will be the implementation graded on, like the runtime complexity, space complexity?
No, so actually what you will be required to produce is outputs. So maybe I should have given an example of a project. So, but the way it will work is you will start off with some problem. You'll try to do a couple of algorithms for this problem. Okay, so an example could be, let's say you have a huge graph and you want to count the number of triangles in it. Okay, so this is one of the standard problems people try to do. And so what you will start with is a paper on this topic. The paper will be presenting some ideas towards it. Okay. You might also try other heuristics of your own choice. Okay. And those kind of things will count towards your grade, and then you kind of produce a report from it. Okay, so you say, okay, I've tried this is what you get. This is a more brute force solution, this took way longer, but this is the numbers we got. So the idea is that you should know how to slightly work with some reasonable sized data set and come up with some report out. Yeah.
The data set will be provided?
Yeah, so that's why we will go with very standard papers, like kind of well-known papers, so that they will have links to data sets and everything. Okay. So this is more of, you have a somewhat non-trivial algorithm and you guys want to, it's good if you know how to implement these things. And doing it on a real data set actually gives you some more confidence in how to play with stuff. So that's the goal of the project. And actually, some of you might even find it easier than some of the homeworks, but it's fine. Okay. All right. So that's homework 3. So another quick announcement. Apparently, there's so you should all know of this data science club. Hopefully, most of you know about it already. Okay. So, and these guys keep having workshops, and this one is by this company called Qualtrics, which apparently one of the leading software companies, yeah, whatever, right? So yeah, so they have some things. So these are some kind of job announcements. So, it will be good if you guys go for some of these things. Okay, if you are looking for internships and things like this. All right. Okay, so back to where we were. Okay, so we were looking at flows, right? So the max flow problem, we're thinking of it as routing from S to T. Think of sending water in pipes. You have edges that have capacities, and you're supposed to find a collection of paths such that you send as much flow as you can from S to T. Okay, so that's the max ST flow problem. And last time I said that one way to think about flows is as a collection of paths. Okay, and another way is just by saying on every edge there is some flow F sub E. Okay, every edge has some capacity which we denoted by C of E. And F is something that needs to be smaller than equal to the capacity. We said that a flow is valid if at every node apart from the source in the sink, the total amount of flow going in is the total amount of flow coming out. Okay? So, and if that is satisfied, then these two notions are equivalent. Okay, so this is what we said last time. And last time we also saw algorithms for it, right? So we kind of the message from last time is that if you just do greedy routing, okay, and what we meant by greedy routing was find a path, route as much flow as possible along that path. Okay, so subtract capacities. So for every edge on that path, you subtract off how much flow you've already sent. Okay, that's like the remaining capacity, and then you try again. And you repeat. So this is a natural algorithm, but we saw an example in which this can get stuck at a non-optimal solution. So there's, we saw this very simple example where you had a graph where the max flow is 2, but greedy got stuck at with a flow of value 1. So that's what we saw. Then we said, okay, so then we said there is this idea of Ford and Fulkerson, and the high level idea is that you can somehow correct the mistakes that greedy has done. Okay, and the way you do this is by what is called the residual graph. Okay, so this is what we defined last time. I'll show you the definition again. And the idea is that if you have any current flow F, F is some current flow you have, by current I mean the present flow from S to T. So you can define this graph which is called the residual graph. I was calling it G sub F. G sub F is because it has the same edges as G and it has some backward edges. Right? That was the residual graph. And the main claim here was that, so you have some current flow F. Okay. Now you construct the residual G sub F. G sub F is another just flow problem. Okay, G sub F is it's another instance of max flow. And what we said is, in this instance, you try to find an ST flow F prime. Okay? And the sum of these two flows is a valid flow in the original graph G. This was the theorem we proved, and it needed two steps. One is you had to check flow conservation, you had to check that none of the capacities were violated. Okay, so I'm just doing a quick recap. So, yeah, so you don't have to fully remember all these details. You can go back to the class. But just for clarity, so what was the residual graph? Okay, so you are given a graph and any valid ST flow F. Okay. Then G sub F is a graph where you have the same edges as before. Okay, so you have if you had an edge E before with capacity C of E, now the capacity becomes C of E minus F of E. And additionally, you have a backward edge of capacity F of E. Okay. So for every edge E in the original graph, you have these two edges now. And I also had mentioned this minor technical thing, like if the original graph had two things, then had edges in both directions, then you add Fe to the opposite side. Okay. So that's what it is. Okay, so this is the residual. And knowing this, the Ford-Fulkerson algorithm is something extremely simple. All it says is you start with the zero flow. Not me, right? Okay. So you start with the zero flow. Okay, and every step you have some flow F. And conceptually what we do is we have this F, then you compute G sub F. And this is the residual graph you computed using this. I mean, this is the definition. And in the residual, you try to find a path. Okay, so you could actually find any flow, but you just try to find one path from S to T, okay, on which you can send a non-zero flow. Okay, that's called an augmenting path. So a path, an ST path, along which we can send non-zero flow. So what happens if you can't find such a path? Yeah, so the algorithm just stops. Okay, so that's why there's a while, and then you set F equals F plus that path F. So and this plus we said is like the edge-wise combination of. So on every edge you do the algebraic sum. Each edge. Algebraic sum of flows. Okay, so this was the algorithm. So we didn't quite see why it was correct, but we kind of saw what the running time is. Okay, so let's now see the correctness. Okay, and the reason we're going to see the correctness is because it's again a very different proof technique. Okay, so this actually, if you've never seen it before, this will look a bit miraculous, okay? And also, I should mention that there is an easier proof for which you can look at the book, but this one I think gives more insight. Okay, so the textbook has a more sleek proof. But this proof kind of does two birds in one shot. Okay, so I also wanted to do what is called max flow min cut theorem. So this proof automatically does. Okay, so all right. So let's see why this algorithm is correct. Okay, so the question we've got to ask ourselves is, so the algorithm stops when there is no flow in the residue, right? So what is the stopping condition? Stops if G sub F has no augmenting path. Where augmenting path, I mean this, right? It's an ST path along which you can send a non-zero flow. Okay, so this is when the algorithm stops. And at this point, we want to say that F is optimal. So we want to say that claim is, if so, value of F is equal to max flow. So any questions on why this is what we need to show? Because all we have to show is at the end of the algorithm, we have an optimal flow. Right? And at the end of the algorithm, you have that condition, and if that condition holds, so we want to say that value of that flow we have is the maximum. So that's by definition so far. Okay, so okay, so now what does it mean that there is no flow, I mean that there is no augmenting path or there is no ST path in the residue? Okay, so we have S out here, we have T out here. Okay, so edges have some flow, and I'm drawing the residual graph G sub F. Okay, so there's some edges, there's some back edges, something going here. And capacities are something like C of E minus F of E, and back edges have something like F of E. Okay, and so you have some things like this going all the way. So what does it mean to say that there's no path? I mean, there's no augmenting path.
There's no path from S to T where every edge has C greater than 0.
Okay, yeah. So what he's saying is that if I look at any path from S to T in this new graph, at least one of those edges will have capacity. The new capacity now is C of E minus F of E. So this has to be less than or equal to 0. Can it be less than 0? No, right? So it has to be equal to 0. So if I look at any path from S to T, okay, then I must have at least one edge with capacity equal to 0. Okay, with the new capacity equal to 0. Okay, so that's what it's saying. Okay, so that's a good observation. So what this means is that on every S to T path, capacity 0. Okay, but capacity is the C of E minus F. So this is a good observation, right? So, and having capacity 0 basically means that for those edges, okay, for those edges, C of E equals F. Okay. So this is one observation. Okay, so let's leave it at that. Okay. So as I said, the proof is a bit surprising. So we'll do a very indirect approach. Okay, so what we're going to do is now define a new problem. Okay, so let's keep this observation. Okay, let's keep it in the back of our mind, and let's look at this new problem. And the problem is the following. Okay, so you are again given a directed graph. Okay, so you are given a directed graph and some source S, some sink T. Okay, and you again, in this case, instead of capacities, you have weights on edges. Okay, so let's call the weight W of T. Okay, so this is just any old directed graph problem, right? So this is some new thing. But the goal in this problem is the following. So you want to delete edges of the smallest, I said the smallest number of edges, but let's say smallest total weight. Okay, so you want to remove edges of smallest total weight. Okay, so every edge has some weight. So in this case, I could decide to remove this guy and this guy. And the goal is to disconnect S from T. So in this sense, it's kind of similar to what we have in the final condition before, right? So our goal is there should now be no path from S to T. So that's the goal in this problem. So for instance, I could even have disconnected this, 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 and this. The sum of these edge weights was smaller than the sum of those two, then this would be better than disconnecting those two edges. So all I want to do is remove edges, edges of the smallest possible total weight, so that S is disconnected from T. There's no path from S to T. Okay, so this is what is called the min cut problem. Okay. And yeah, so now I'm going to do something interesting. Okay. So first I want to make a simple observation that connects the flow problem to the cut problem. Okay, so first, is the definition of this problem clear? Any questions? Like if all edges had weight 1, what would you have to do in this case? Yeah, in this case I think just removing these two edges is probably the best, because yeah, after that it looks like you have to remove 3 edges. Okay, because T has 3 edges. Okay, so or you could have a graph where something like this holds. I mean, you could have and here, I mean, to disconnect S from T, all you got to do is remove this edge. Okay, also you could have edges like this, right? So it doesn't matter. So all you want to make sure is there's no path going from S to T. So yeah.
So my only clarification, we're not removing the edges of smallest weight. We're just removing any edge such that we can disconnect.
Yeah. So the goal is the sum of weights of the edges you removed needs to be minimized.
Okay.
Okay, so that's part of the objective. Okay, so in this case, for instance, maybe this edge had a really large weight, then maybe it might actually be better to remove this and this, if this had much larger weight than these two. Okay. So, yeah. So this is the statement of the problem. Okay, so why did we introduce this problem? I want to say that this problem has one easy connection to max flow. Okay, and the point is this. Okay, so first, we want to ask, suppose I have a max flow problem. Okay, so I have a graph and I have capacities now. Okay, so G is instance of max flow. Okay, so here the goal is to send as much flow as possible while respecting capacities. Right? That's the definition of max flow. Now suppose I just treat capacities as weights. Treat capacities as weight. And just come up with a min cut instance. Okay, so I just say, okay, this is now the weight. The weight is equal to the capacity, and now try to remove as few edges as possible, so that S is disconnected from T. Okay, so let's call this the min cut of G. Okay, so that's the answer. Okay, so I want to say this is the smallest total weight of edges, smallest total weight that disconnects T from S. Okay, so what I want to ask is, can you have a flow in this graph that's larger than the minimum cut? So what I mean is, suppose, let's put some values, right? So suppose I construct this very simple graph that I had before. Okay, all edges have, let's say, capacity 1. In this case, here's a cut of value 1. Okay, because I've just removed one edge. Now, can there be a flow in this graph from S to T of value bigger than 1? And why not?
Because that's the bottleneck for one.
Yeah, because a cut essentially captures a bottleneck, right? So a cut basically says, okay, let's say this is the cut, or sometimes you could have a more complicated cut, like in this case, maybe, in this case, could be the bottleneck, potentially. Now we are saying that if I remove those edges, then there's no path from S to T. Now look at any possible flow. The most it could have done is flood all those edges, right? The most it could have done is have those edges flowing to capacity. And in that case, the amount of flow going from the S side of the cut to the T side of the cut is at most the sum of these edges. So what I want to claim here is that max flow in the graph is less than or equal to the min cut. Okay. And in fact, more is true, right? So you can say that for any flow, value of the flow is less than or equal to value of any possible cut. Okay, so I'm just choosing the min cut, but I could have chosen any other cut. I would still have that the value of the maximum possible flow is less than or equal to the value of that cut. Okay. So that's what I'm saying. So the max flow is less than or equal to the min cut in G. Okay, so any questions on this? So far most of this is very intuitive, but maybe the notation has put you off, so I'll wait for a bit. So, yeah.
Would it be less than equal to, would it be any time the max flow would be less than the min cut?
That's what we are going to show, but so far what I have proved with this reasoning is that no flow can be bigger than or equal to, can be larger than the minimum cut, right? Because a cut represents a bottleneck. It's, if you remove those edges, there can be no flow from S to T. And and that's all I'm saying so far. So far I've just established that max flow is less than or equal to the min cut. Now I want to, so this is where, this is how I want to show the correctness of Ford-Fulkerson. Okay? So what I want to show is, I'm going to show that the final flow we end up with in Ford-Fulkerson actually has a cut of value equal to the value of that flow. Okay, so the proof strategy is for the flow we end up with in Ford-Fulkerson algorithm, there exists a cut in G such that the flow, let's call this flow F. There is a cut such that let's call this cut so S is a set of edges. Okay, this is a set of edges, subset of edges, whose removal disconnects T from S, right? The usual definition. So that's the thing, and so it's cost of S. Cost of S is sum of the edge weights of the edges in S. And this is going to be the strategy. Okay, so we are going to show that for the F that we end up with, there exists some cut, so that value of this flow is equal to the cost of this cut. And why is this enough?
Because it can't be more.
Yeah, so what we've shown in this previous slide is that even the largest possible flow, okay, so if you think of writing down all the values of, so this is the real line, let's say. Okay, so this is the set of real numbers. So there's some flow with F which has value equal to this, maybe there's some other flow F prime that has value this, and so on. And there's the maximum flow. Okay, so this is something. And now you might have some cut S that is out here, you might have some other cut that is S prime out here, and so on. And then there is the minimum cut, right? So let's call this S star. The previous slide we said that F star is less than or equal to S star. Okay. So the previous slide said that the max flow is less than or equal to the min cut. Okay, so this is what we said. And now what we are saying is, I find you a flow, okay, so let's call this F, where there is actually a cut whose value is this. And what's the only way this could happen? Okay, so I'm saying that there is a value, there is a flow here, and there's also an S out here, okay, whose value is equal to the value of this F.
Has to be the max flow and the min cut.
Yeah, so the only way this can happen is if these two are literally at the boundary and the boundaries actually coincide. Okay, so that's why I said it's kind of a magical proof, because it's saying that you have some sequence of numbers. And I'm saying that the max of this sequence is less than or equal to the min of this other sequence of numbers. Okay. And then I'm telling you that, hey, here is the flow that I've ended up with. For this, there's a corresponding value here which are equal. And so the only way that can happen is if these two sequences meet at this point, and this is actually the max. So that's actually the very nice idea behind the correctness of Ford-Fulkerson. Okay. And if we can show this, this also establishes what he just mentioned, which is that, so this is what is called the max flow min cut theorem. Flow min cut theorem. That in any graph G, the max flow is equal to the min cut. So earlier we could only show that the max flow is less than or equal to the min cut, but so note that this is a very indirect argument also, right? So we are saying here is this algorithm, here is the Ford-Fulkerson algorithm. Okay. I'm going to somehow prove to you that the end point of this Ford-Fulkerson algorithm, the F that you end up with in this Ford-Fulkerson algorithm, has some cut associated with it, such that the value of the flow is equal to the value of the cut. Okay. And that will show, because of the fact that any flow is less than or equal to any cut, that this is actually the max flow, and in fact in the graph the max flow is equal to the min cut. Okay, so that's why this is a nice way of showing things. That's why I was saying it's very nice the first time you see it. Okay, so I'm going to pause here. We still need to prove this. Okay, so we are going to show that for the flow that we end up with, there exists some cut as the value of the flow. Yeah.
So basically what we are trying to like say here is like the min flow can go from like a maximum value to a lesser value, and the max flow can go from a
Min cut,
minimum value to a great higher value. And the point that they meet is where they are equal. And
Yes.
the max flow cannot go beyond that, and the min flow cannot drop beyond that.
Yeah. Okay. And yeah, a priori it's not clear that both of them converge to the same thing. Okay, so that's the nice thing. So, and that's what this Ford-Fulkerson algorithm actually gives you, because for the endpoint of this algorithm, you'll be able to show that there's actually a matching cut, and that's why. Okay, so, right, good. So this is what we need to show now. Okay, so for the flow that we end up with, there exists a cut such that value of the flow is equal to 1. Yeah.
Excuse me, how can we show that the maximum flow will not be greater than
The maximum flow, oh yeah. So that was actually in this slide, right? So what I said is, suppose I take any cut, okay? And in particular, let's take the min cut. So what's the definition of the min cut, right? So it's some set of edges whose removal disconnects T from S, right? So suppose I go ahead and remove all those edges. Okay, so this is S, this is T. Okay, these are a few edges, and I remove them. Now let's look at any flow from S to T. Okay. So what's the most that it could be? I mean, we know that there's no other path from S to T, because otherwise it's not a cut. Okay. So there's no other flow and there's no other thing. So any path must actually involve these edges. Okay. So now, what is the most amount of flow I can send on this edge? By definition, it's the weight of that edge, right? Or it's the capacity or weight of that edge. Yeah, I'm saying that I set the capacity equal to the weight. So it's equal to the capacity. Okay, on this edge, so think of the cut as dividing a graph into two portions. One is the S portion, one is the T portion. Now think of something flowing in this graph. So let's think of like water or something like this flowing from this graph. I'm saying that this edge can carry only some capacity of E amounts of flow. Okay, so if this is E1, capacity of E1 amounts of flow, this edge can be carrying a total of capacity of E2 on it from one side to the other, and so on. Therefore, the total flow going from one side to the other can only be at most the sum of the capacities. Okay, so that's why there can't be a flow that is bigger than a cut. Okay, and that's the next thing. Yeah.
So I can imagine it for a one cut, like when we're doing it for one edge, but I cannot imagine it for multiple edges.
What do you mean?
There can be a situation where we are to eliminate multiple edges. So
Yes.
will this max flow min cut will converge even in that case?
Yeah. So I mean, it converts in any graph, right? So well, all I'm saying is, let's take a complicated example. Okay. So okay, so let's take an example where, I mean, you've got to cut multiple edges. Here there's no single bottleneck edge, right? And maybe there's also. So here presumably if I cut, okay, one way to say this is by saying, okay, if I cut I'm trying to find a non-trivial cut here. Okay, an easy cut would be one of those sides, but I'm trying to avoid that. Okay, so okay, but let's take any other cut. Let's say, it doesn't have to be a minimum cut, right? So let's do this, this, and this. Actually, this still leaves a path, so okay, never mind. So let's just stick with these three. Okay. So suppose this happens to be the min cut in this case. Okay. So now what I'm saying is removal of these three edges results in no flow from S to T. No possible path from S to T. Okay. And formally what I'm saying is this now divides the graph into two portions. You can look at S and everybody reachable from S, okay, using some path. After removing these edges, there are these other edges, right? So you can look at everybody who is reachable from S. T is not one of them, right? So maybe some of these guys are reachable from S. Okay. And T is outside. Okay. And by definition, any edge that goes out of this, I have already cut this edge. Why is that? Not just edges to T, but any edge that goes out of this set S. Yeah, no, that's the definition of this circle. Okay, so this circle is all vertices reachable in G, reachable from S. So it's nothing that you can. So if this edge was not cut, then this vertex should have been included in this set, okay, because that would be reachable from S. Okay. So that's why all the edges going out of this set are actually cut. Alright, so now I want to say that if I look at, so these are actually multiple edges. Okay, so I want to say that there can't be a flow from S to T of value more than the sum of these edge weights. Okay. And that in some sense follows from flow conservation. Okay. Flow leaves S, okay, and it goes somewhere, it reaches all these vertices. But to get out of this ball and get to T, you've got to use you only have those edges. All those edges have been cut. And so the sum of the capacities of those edges is an upper bound on the amount of flow that could be coming out of this. Okay. So if you think somewhat like a physicist, there's this, you have this ball and you look at the net outflow from this ball, right? So, and what we're saying is net outflow can only be equal to the sum of the edges going out, because those are the capacities. Okay. So net outflow from this ball less than or equal to sum of weights of cut edges. And net outflow is equal to the flow from S to T. So that's any other information? Yeah.
So we will always cut those edges that directly connect T.
No, so that's why I was saying this is probably not the best of examples. So for instance, you could have a situation where it's two edges that need to be cut, and here there's multiple things that goes there. And T is out here. Okay, so in this case, these two edges are the best ones to cut. Okay. And in this case, that ball will basically be all of these vertices. Okay. And that's how we define this ball. That's a good question. Alright, good. So now we are almost at the end of the proof. Okay, so this is proof that max flow is less than or equal to the min cut. And now I want to show that for the flow that we end up with in Ford-Fulkerson, there's actually going to be a cut of the same size. For this, we are essentially going to use the observation that we had before. Okay, so this is what he was mentioning, that suppose I look at where this Ford-Fulkerson ends up with a flow F, where in the residual there is no path from S to T. So this was the residual graph. So I just had capacity C of E minus F of E. Okay. Now, let's say I remove all these zero weight edges. Okay. Now this, okay, actually let me be more formal because otherwise I will have to do the same way. So yeah, so let's look at S and T. Okay, so F is the end point, end state for Ford-Fulkerson. Now what we are saying is, now there is no augmenting path. So if I draw the residual graph G sub F, so all the, I have these guys, have some edges whose capacity is 0. So C of E minus F is 0. So I remove those edges. I mean, you don't literally need to remove it, but yeah, think of removing it. Okay. So now I want to define a ball the same way I did before. I want to say, let's define capital S to be set of vertices. So that are reachable from S using edges of weight more than 0. Okay, of capacity minus. Okay, so you have this residual graph. The residual graph, I'm trying to draw a ball just the way I did before. I'm going to look at all the vertices that I can reach using edges of weight strictly bigger than 0. Yeah.
The question is like, isn't this the balls that we will draw?
Mm-hmm.
They will be a subset of all the edges. So they will be like in an exponential domain.
Yeah. I mean, that's fine. You don't need, I mean, this is all just in the analysis, right? So how does it matter that there's a lot of, yeah. And also, this is easy to construct, right? If I give you a residual graph, you do BFS or something, and go as long as you have a non-zero, I mean, a strictly positive edge, right? And you will find the connected component essentially, right? So you will reach some vertices. Beyond that, you will not reach. Okay. But what we know for sure is that T is in the sets that you cannot reach. Okay. And every edge that was out, I mean that was going out of this set S, actually must have capacity 0, because otherwise you could have gone out. So this is, yeah, so this is the argument. So the observation, there's two observations. T is not in S. Okay. If so, you could have found an augmenting path. By definition, there's no, right? And all edges out of S have C of E equals F of E. Okay. So, and this is essentially the proof, right? Because what we are saying is, now if I cut all, I mean, now let's go back to the original graph G. And here all those edges had capacities C of E equals to, I mean, it had all these capacities. It had capacity C of E. Suppose I think of cutting all those. And now there is no flow from S to T here. So in some sense, for the flow F, I have come up with a ball such that if I cut all the edges out of that ball, then I mean, essentially we have C of E equals F of E for all of those edges. Therefore, sum over all those edges, E in E going out of S. C of E equals sum over the same E, F of E. This is the net outflow from S. And this is equal to the value of the cut. So what we've established is that there's some set S of vertices. You look at all the edges going outside. There's, the total F that goes outside is actually equal to the flow from S to T. And the value of that flow is equal to the value of this cut. So that's exactly what you established, and this is what we wanted, right? So for the flow that you end up with, you produced a cut that has the same value as the flow. And that essentially completes the proof. So yeah, so that shows that for the flow that we end up with, there exists a cut, so the value of F equals constant. And the reason is that all these zero edges have this property that the capacity is equal to the flow. And that's why if I remove those things, the flow is, the sum of the flows is equal to the sum of capacities, and that's the net outflow, and that's what it is. Yeah.
So is there an algorithm for finding the minimum cut that's better than this for?
Oh yeah, so that's a great question. There are algorithms that are better than this, but they are much more complicated. So yeah. So if you think about it, it's not that complicated, but yes. We will actually see one when we go to randomized algorithms. Okay, that's like 2 weeks from now. Yeah.
So it's like for the ball, we will not have to consider all the edges, just the edges which sum up to 0. Subsets of edges which sum up to 0. Where CE minus FE is equal to 0 for cuts.
Right. So all I'm saying is, in some sense, if CE minus F of E is equal to 0, then you can't send any more flow, right? So vertices outside are not reachable.
Yeah. So if we are to iterate over all the possible things, we will only iterate over C's, where C of E minus F of E is equal to 0.
No, there's no iteration. I don't understand. So what do you mean by?
So I'm asking.
How do we come up with this set S?
Yeah.
Okay. So the way we come up is the following. So you have this residual graph, right? Some edges are 0, some edges are non-zero. Start with S, do a BFS, and look at everybody who is reachable using non-zero edge weights, positive edge weights. Okay? Actually, positive is the right word, not non-zero. Yeah, negative is different. So look at everybody who is reachable with positive edge weight. That is S. That's it. So you just do a BFS to get S. Okay. So any other? And that's why he was saying that you can use this as an algorithm for cut itself, because find this S, this is the min cut.
Two questions. The first one is why the sum of the CE equals the value of the cut, and the second question is that since we can directly prove that the cut equals the max flow, why we need to prove that the max flow will not greater than the cut before? We can just prove that they are the same.
No, so we don't know that this is the max flow, right? So this is just the output of, so there's multiple things going on here. So we came up with this Ford-Fulkerson algorithm. This ends up with some flow. We don't know that this is the max flow. That's part of what we are trying to establish. Okay? So, and the way we are doing it is kind of devious. So we introduced this new problem, which we called the min cut problem. We said that the optimum for the min cut is always bigger than or equal to the optimum for the max flow. Then we are saying that for the output of Ford-Fulkerson, there is actually a cut whose value is equal. So in particular, the optimum of these two problems must be the same, and also Ford-Fulkerson must be optimal. Okay, so it establishes two things in the same shot. Okay, so that's what I was saying.
Why the sum of the CE equals the value of the cut?
Why is the sum? Well, the sum of the CE is the definition of the value of the cut. I guess you mean why is the sum of the CE equals to the sum of the FE? I mean, the definition of cut is the sum of the costs of the edges on it, right?
So it is not the minimum cut.
Oh, right. This need not even be the minimum cut. Yeah. So that's the thing. You come up with some cut whose value is equal to the value of this flow, and that automatically implies it has to be the minimum cut. So, yeah. So that's nice. Okay. So this is actually a more general phenomenon called duality, which we will see. Okay. So this max flow and min cut are what are called dual problems, and value of one will always be less than the value of the other. Their optima will coincide. So, all right. So that's the, yeah.
So why do you have to do BFS to find S? Why can't you just say cut all the edges where C of E minus FB equals 0?
You could do that, but how do you, so actually you had to argue that the net outflow from this set is equal to the sum of the edges cut. For that you needed this, you need something like this. Because you need to come up with a set of vertices such that the net outflow from this is what you are interested in. Yeah, but were you going to say something?
Oh, well, so I actually was thinking of doing it that way, but if you have two edges in a row that are both 0, without doing the set cut, your cut's not it's going to be too big, because you're going to cut two edges.
Yeah, if you remove all these edges, you could sometimes break up the graph into more than 2 pieces. Alright, so that's that. And the running time, this is something we saw last time. Okay. So actually, before we go ahead, so any other questions on the correctness? So this again is another example of a non-trivial proof. We saw been seeing some of those lately, like spanning trees was nice, and this also is clever. Yeah.
Why does this proof do not work for the simple greedy algorithm?
Oh, that's a great question. So you should try it. I mean, in the sense that in the simple greedy algorithm, this relied on the fact that we are working with the residue. Okay, so look at this argument, right? So here, you were working with this residual graph where you had edge weight C of E minus F of E. If you looked at that example where greedy failed, so you will find that there is still a path from S to T in the residue. Okay, and that's why this proof won't work. But that's a very good point. All right. So, and last time I told you that this algorithm is nice, but it could be pretty slow, in the sense that if you have edge weights that are really large, then you might actually end up taking running time that is proportional to that. So you might wonder, can this actually happen? The answer is yes. I had an example, but I'm not going to do it because I want to do all this stuff. Okay, so I will put it up somewhere. I mean, it's a very standard example. So you can also find it in the textbook. So this bad running time can actually happen. And there's actually ways to get around this also. Okay. Actually, maybe I should say the way to get around this. So here I was saying, do you guys remember this discussion, or should I summarize this again? This is what we saw last time. So last time we tried to see how long can this algorithm take. Right? We said that the algorithm just tries an augmenting path. It tries some augmenting path, right? And it could be that the amount of flow you augment is actually really tiny in each iteration, which means that you end up taking a huge number of iterations. We said that if your weights are all integers from 0 to c, you could end up taking roughly n times c iterations. And c could be huge, c could be like 2 to the n. Yeah, that's why this is not so great. And there's two very simple ways to avoid it. And one way is, when you find an augmenting path, find the augmenting path that gives you the most amount of flow. Okay. That's one way to avoid this problem. Then you can actually prove that you just get something that looks like poly n times log c. So that's something you can prove. Okay. And also, if you actually take the shortest length path, augmenting path, where length is the number of hops. So it sounds surprising, but that actually also works. Okay, then you don't even get some dependence on log c. You just get poly n. So that's another nice fact. Okay, but we don't. Yeah, let's not go into that. That's actually flows. There can be an entire course on flows. Like Bob Tarjan used to do this. So you would have a full algorithms course just on flows, right? But we are not. Yeah, we don't want to get there. Okay, so. Yeah, so let's not go there, but there are simple tricks to avoid this running time. Okay, so that's the bottom line. Alright, but what I want to do is a couple of applications of flows, okay, before we get next class. One is the Santa Claus issue that we've seen in homework and also in class before. We saw this in the context of local search. So do you guys remember this problem? You have children and gifts, and oh yeah, it should be fresh for you guys given that you submitted homework on Friday. Okay, so you have children and gifts. So actually, just intro. So what I want to do now is, there's some problems that don't obviously look like flows, but it turns out there's a simple reduction to flows. Okay, and that's what I want to now get at. So that's the context. And one example is this problem. Okay, so you had gifts, you had children. Each child had some edge weight. So these are some A, I, J. This is the value that child I gives to gift J. Okay, so yeah, so how do you cast this as, I mean, so, and what is the goal here? The goal is find the best in terms of total happiness. Assignment of gifts to children. Okay, so this is the goal, right? So can you view this somehow as a flow problem? Yeah.
Maybe we can add like 2 modes.
Yeah, so this is what you would guess. For a flow, you need a source and a sink, right? So this problem as such has no obvious source or sink. So let's add a source and sink. Okay, so What is source, what is sink?
I mean, gifts can be source, right?
Okay, so you can be source and sink T. I mean, we are thinking of giving gifts, so let's assume that you have edges that go like this. Giving gift j to child I gives value of aij. So that would be that. And I want to add, I want to add a source and a sink. Okay. And now, what is the, how do you capture this as a max flow?
Connected as to all of the gifts.
Okay.
With large weight.
Okay. So
if the edge have I guess a small capacity.
we want a small capacity.
Yeah.
Okay. Like capacity 1.
Yeah. Capacity will just have all of the A, I, J.
Okay, so can I do 0?
Yeah.
Okay, fine. So suppose you did this, right? And what about this T? Presumably you want to do this also. And what about capacities here? Okay, let's try 0 again. Okay, so now what is the max flow from S to T? 0, okay. So doesn't tell you much about the cut. I mean, that doesn't tell you much about assignment, right? So, okay, so what if, so I guess what if you had,
You can have one. Edge weights of one.
on these guys? So if you had 1, what about here also 1? So, now what happens?
No, half a large actually.
Yeah, so actually max flow in this case is not something we can very clearly say, right? Because it's, if the AIJs are huge, right? So if the AIJs are huge, then somehow cutting these is the best and you get an answer of n, which doesn't tell you much about how you assign gifts to children.
Maximum weight.
Yeah, so let's say I make it max over I AIJ, or for convenience let me write infinity. Okay, so you just have infinite weight. In this graph, what is the maximum amount of flow that you can have?
The maximum value of the gift that a child can get.
Why is that?
Sorry.
The max cut would be max flow.
That's
Max flow.
What prevents me from having, so suppose I have a graph where this is 1, this is 2, this is 1, and okay, these are infinity, let's say. I could always send a flow of 1 plus, I mean, there's no matching. I could think of sending, I could have flow of 3 here, 3 here. I could do 1 here, 2 here, 2 here.
But one gift can only go to one child.
So how do you enforce that? I mean, as such, the instance that you've created allows you to have multiple things.
only one way in,
Sorry?
like only one way in for a node.
But which one do you pick?
The max. For a particular gift.
Would that always work? I mean, you
No,
come up with
actually.
it. Yeah. So. Okay. So. Yeah. So you can think about this. Okay. So. What if I told you that somehow the edge weights are not so bad? They all, all AIJs are within a factor 1.5 of 1 another. Then can you think of something? Like all edge weights are between 1 and 1.5. Can you think of how you could do this?
If we are getting any value for a particular node which is higher than 1.5, then we are not to consider that flow.
Right, so I mean actually I think I made a mistake. So I don't think this will work. So only if edge weights are 0 or 1, I mean you can actually, that's what I had in mind in some sense. Okay, so what if I told you that all Aij are either 0 or 1? Yeah, they should not be between a small range. What if they're between 1 and 1.5? You can see that the same problem can actually happen. Okay, because you can send like 1.5 here and then you can send 0.5 along different ends and so on.
So just choose one for all. Maybe we can normalize.
Yeah, so then what you can do is what you're saying, that you just choose a capacity of 1 here. Okay, and a capacity of 1 for these guys.
Yeah.
And I want to claim that this actually gives you the best total happiness. Okay. Can you say sure?
Because one can't be split up into 0.5.
You could.
I could actually. But the outflow is also 1.
But we decide the step size, like we decide what flow goes in, right? For a max flow. So we can always set that up as 1.
Yeah, so I think what you're trying to say is, suppose I just follow the algorithm. Okay? What is the algorithm doing? It's basically finding augmenting paths. Okay? And it's constructing the residual, and it's finding the augmenting paths, constructing the residual, and so on. And if you think about it, the first time I will always send at least 1 unit of flow. Okay, I'll send 1, not 0. And at every step this remains true. Okay, so you either send 1 unit of flow or you send 0, at which point there is no augmenting path. Okay, so all the assignments you will make will end up being integers. So that's the first observation. Okay, so I should call this. Yeah, so it turns out doing a reduction for the weighted case is actually trickier to flows. So that's why unweighted matching is the typical example that we give. Okay, so it's max bipartite matching. Oh, let me not introduce the name. Okay, so it's unnecessary. Okay, so if all edge weights are all Aij are 0, 1, then what we are saying is, if you follow Ford-Fulkerson algorithm, then you end up with integer flows, and that too 0 or 1. In each iteration. So which means that the capacities in the residual graph are all integral throughout. And this means that any flow you find is also an integer flow. And then you can convince yourself that you can't have a 2 here. So, I mean, the capacities of these edges are only 1. Therefore, everything has to be 0 or 1. There can't be 2 units of flow flowing into any vertex, because by flow conservation, then this would have to be 2. Okay, but the capacity there is only 1. Okay. So this is just one example. Okay, so this is called unweighted bipartite matching. And the other application is something that I mean, this is also a nice application of flow. It's what is called the edge connectivity problem. And the idea behind this is if you have some communication network, then in some sense, how many edges do I have to remove to disconnect this graph? And this again, if you follow this max flow min cut example, this is basically like the min cut, right? If I gave you S and T, then it's like the min cut. Here I'm basically not giving you S or T, so you can basically try all possible S. Okay, so this is what is called the edge connectivity. This is another classic example of flow. And in general, when we try to reduce a problem to flow, this is the kind of thing you're looking for. Okay, so you want to come up with a graph, and you want to come up with a source and a sink, and you want to say that okay, this if I look at the max flow, it's going to tell me something about the solution to the original problem. Okay. So like in this case, if I had weights being 0 or 1, then the max flow will allow me to read off the optimal assignment of gifts to children. So, yeah.
But if only weight zeros and ones are allowed, then how will we know which flow is max? Because any flow will have the same value.
No, right? Because what if I told you that some child could just get a gift of value, his value could be 0. Right? Because what if I told you that this weight is 1, this is 0, this is 0. And this one is 1 also.
But how am I bringing the happiness value into
so the happiness value for the best, the best assignment in this example is this gift goes to this child, and this one goes to here, but the total value is only 1, it's not 2. Okay? Because this child has happiness value 0.
So while calculating flow, we also calculate value the happiness based on the flow generated.
No, right? So that's the thing. So the argument will be that just view this as a flow problem, solve it to optimality. You will have some values of the flow. Okay? And in this case, what will the best flow look like? It will just have one path that goes from here to here. Okay? And that's it. Right? And this will have capacity 1. And all the children who are, so everybody, so you assign that gift to this child. And presumably there's other things like this in general, maybe this is there, but this child is left without any gift, without any flow coming in. Then you basically, what you know is that there's no way you can give them a gift that is valuable to them. Okay, because all values are 0 or 1. So, so that's the solution. So the idea is you solve flow to optimality, you have the final solution. You want to argue that the final solution lets you read off something about the problem that you actually wanted to solve. So you'll see more examples of this in your homework, so it's good to understand this example. So,
no, but in the optimal case, I'll just have one path, right?
So in this example, so you'll have one path. What does it mean that there's no path via one of these other guys? This means that there is no, there's no way you can assign a valuable gift to this person. Which means that you can assign anything else that's left over, and it's fine. They anyway have gift value 0. Because if there was a gift of value 1 that was unassigned to anybody else, which you could have given to this guy, then there would have been an augmenting path. Okay. So for that reason, that's why this. Think about it for a minute. You will realize why this is scary. But that's a good question. So when we reduce something to flow, you always assume that you solve the flow problem. Solve the flow problem. And opt flow allows us to read off the desired solution to desired problem. Answer. Desired. Okay. So sometimes it might not you might have to do something non-trivial to construct the answers, but very often you can just read off. So good. So let's stop here. I was hoping to also do a little bit about empty completeness, but we'll do that next time and after the